Alright, so we're going to continue talking about acids and bases in this video, and specifically about pH and pOH. So we can measure the acidity or alkalinity of a solution, and we do this using the pH scale. The pH scale ranges from 0 to 14, and pure water is neutral at pH 7. If you have a number greater than 7, that means it's basic. If it's less than 7, it makes it acidic. Another comment I'd add into this is this scale is logarithmic, and so that means that going from 1 to 2 or like 2 to 1 on acidity, that's a 10 times difference. So for example, hydrochloric acid or your stomach acid, to something like lemon juice. So if hydrochloric acid is pH 0 and lemon juice is pH 2, that's a 10 and then 100 times difference in acidity, because that's how logs work. They're based on base 10. So every value we go over is 10 times more. So from stomach acid to an apple, that's 10, 100, over 1,000 times difference. So while it might not seem significant, 1 to 2, like, oh, that doesn't seem like it'd be a big jump, it's actually a huge jump. All right. So these are some common acids and bases along the scale. So like I said, hydrochloric acid is down here at the very end. We see lemon juice and vinegar around 2 and 3. Some were surprised at how acidic a banana is at almost 5. Milk is slightly acidic. Water is neutral. And your blood is slightly basic. Baking soda is a basic solution, like we said in the class last time. And in fact, if you're struggling with like indigestion or acid reflux, you can drink a little bit of water with baking soda in it. It's disgusting, but that can help to relieve indigestion. Soap is at 10. Ammonia, that glass cleaner we talked about, is getting more basic, and then drain cleaner is especially basic. So don't be a Heather and poison your friends with drain cleaner, because it will kill them. So when we measure pH, we can use a digital pH meter. You'll see people like landscapers or plant scientists, they tend to use digital pH meters to measure the acidity of the soil, since each plant likes to have a certain acidity to it. So it's like if you're growing a lemon tree, you want more acidic soil, versus other vegetables are going to want more of a neutral soil. So you can use a digital one. We also can use pH indicators, and these are chemicals that change color at different pH levels. So an example of that would be like pH paper. So what you would do is you would take a little piece of this paper, dip it in your solution, and then compare the color of what the paper turns to the pH that it is. You would also see something like this, like if you have ever watched someone test the pH of a pool, they would have a little dipstick that they would put in the water and then compare it to the side of the container. And then you can have chemical ones that you put into solutions. So phenolphthalein turns pink in a basic solution, but will be colorless in an acidic or neutral solution. And then, but there are chemical indicators for if you have an acidic solution, or if you want to indicate when an acidic solution's gone to neutral, or have gone out of the range that you're particularly looking at. You would remember this. You might remember this one from bio class when you did the pink disease with the test tubes and to show like how diseases spread. All right. So to calculate pH, it is the negative log of the H+ concentration. As a note, pH has no units, it's just a number. And then a separate note, I know we don't do what is it, significant digits in this class, or significant figures, but when you take the log of something, you actually get to add on a significant digit. So if you only are given one digit, then you would report 2 digits. But like I said, we don't do significant digits in this class, so I wouldn't stress about that. It's just if you go on further in science, it's just something to note. And then, but remember, never do a calculator dump in this class. Keep your digits within a reasonable range. If you're going beyond 4, then you've probably gone too far. All right, so let's do some calculations on these. All right, so if we have a concentration of H plus that is 3 times 10 to the negative 4, I'm going to, make this bigger. All right, so if we have 3 times 10 to the negative 4, we're going to take the negative log of that value. And that's going to be, so you plug it into your calculator by doing the little negative sign next to the decimal, hit log, and then I would do 3 second EE negative 4 and parentheses, and you would get 3.5 as your pH. Right. Let's try this with the next 2. So you're going to have negative log of 2.5 times 10 to the negative 9. Again, I would enter this in by hitting the little negative symbol, then log, and then 2.5 second EE negative 9 and parentheses, and you'd get 8.60. All right, and the last one, you take negative log again of 5 times 10 to the negative 6, plug it into your calculator, and you would get 5.3. A way to check your answers is, you should notice here, all of these answers are within 1 of their exponent. So, right, 3.5 is within 1 of 4, 8.6 is within 1 of 9. Sorry, this last one here should be 5.3. And 5.3 is within 1 of 6. So it's just kind of a way to check to make sure you plugged it in correctly, that it's usually within 1 of your exponent. All right, so let's look at a real-world problem of calculating pH. So the question is, what is the pH of a 5.3 times 10 to the negative 2 molar solution of HCl? Okay, so with these, the first thing you're going to want to do is write the dissociation equation of your compound. So in this case, we have HCl. And as a reminder, dissociation is when we put a ionic compound, or an acid or base in this case, into water, they're going to separate from each other. And that separation is called dissociation. So when we write the dissociation equation, we're actually just writing how they split apart. So HCl is going to split apart into H plus and Cl minus. All right. When it dissociates, the concentration of HCl is actually going to be equal to the concentration of H plus, and that is also equal to the concentration of Cl minus. But we don't really care about the concentration of Cl minus in this question. We only care about the concentration of H plus. And the way to think about this is, if you have a pen with a cap, and then you take the cap off, you still have 1 pen and 1 cap, right? It's not that you magically have doubled it or halved the amount you have, you've just split it apart. All right? So now we want to find the pH. As you recall, the pH is equal to the negative log of the H plus concentration. So we'll take the negative log of 5.3 times 10 to the negative 2, and that is equal to 1.28. Right? Okay. So sometimes when we're we'll often be dealing with bases, and since bases don't make H+, we can't directly, we don't calculate the pH of it, or we don't calculate it directly from H+ concentration because that's going to be harder to find. Instead, what we do is, because bases produce OH, we calculate the pOH instead. And the equation's the same. So pOH equals negative log of OH minus. And this is actually something you'll see often in science, is if you see this P in front of something, that P means that you took the negative log of whatever it's next to. So in this case, OH. If you go on in science, you will sometimes talk about Ka, and they'll talk about the pKa scale. And so what that would mean is that you took the negative log of Ka. In this class, we're just going to be dealing with pOH and pH, but they mean the same thing. When you see that P, it means that you took the negative log of what it was. So in this case, the concentration of OH. So let's do a couple of pOH problems. All right. So we'll start with this first one here. What is the pOH if OH minus, if the concentration of OH minus is 2 times 10 to the negative 3? So we're going to take the negative log of 2 times 10 to the negative 3, and you get 2.7. Right. Let's do a couple real-world problems. All right, so what is the pOH of a 2.0 times 10 to the negative 4 molar solution of sodium hydroxide? Just like with the hydrochloric acid example, we're first going to write the dissociation equation. So sodium hydroxide breaks down into sodium ions and hydroxide ions. And the concentration of our sodium hydroxide is going to be the same concentration of our OH minus, right? Because for every 1 sodium hydroxide, 1 OH minus was produced. All right. So now we're going to take, so for the pOH, we're going to take the negative log of 2.0 times 10 to the negative 4. And so that is 3.70. All right. Okay, this last one is a bit trickier. What is the pOH of a 2.0 times 10 to the 4 molar solution of calcium hydroxide? So calcium hydroxide breaks down into calcium ions and OH minus ions. And we have to balance these, right? Because on the reactant side, we have 2 hydroxide ions. So on the product side, we're also going to have 2 hydroxide ions. It's just that instead of it being in the subscript form, now it's a coefficient. Okay. What this means practically for you now is the OH minus concentration is going to actually be 2 times the concentration of calcium hydroxide, because we've produced 2, right, because of this 2 here, it means that we're doubling, we would need to double this concentration, because for every one of these, for every one of the calcium hydroxides that were put in, we got 2 OH minuses coming out. So this would then be 2 times 2.0 times 10 to the negative 4. So that equals, so that makes the OH minus concentration equal to 4.0 times 10 to the negative 4 molar. Okay. So to find the pOH, we're going to take the negative log of 4.0 times 10 to the negative 4. So that is 3.7. 0.40. And look at that. So even though we doubled the concentration between this first problem here. So right, we had so this concentration of hydroxide from calcium hydroxide is twice that of the sodium hydroxide. But it only made it what it looks like a little bit more basic, right? Because it only has a difference of 0.3. But remember, because logs are on a scale of tens, or magnitudes of tens different, that's actually a more significant change than it might look like. So even just 0.1 change makes a big difference when it comes to pH and pOH. So let's put this all together. So we can use the pOH to find the pH of any solution. And this is because pH plus pOH equals 14. The way this comes from, remember that the scale goes up to 14 and water is neutral at 7. And water breaks down, so H2O breaks down to H plus and OH minus. So if pH of water is 7, and it can go up to 14, then that's going to make the pOH of water also 7. So they're always going to add up to 14. But if you're going from one to the other, what you do is you subtract the other one to the other side. So in this case, pH is, if we have pOH and we're looking for pH would be equal to 14 minus pOH. Okay, so let's do a problem of this. So what is the pH of a 5.0 times 10 to the negative 5 molar solution of sodium hydroxide? So again, sodium hydroxide dissociates into sodium ions and hydroxide ions. Sodium hydroxide and hydroxide are 1:1, so the concentration of sodium hydroxide is going to be equal to the concentration of our hydroxide ions. So pOH is going to be equal to the negative log of 5.0 times 10 to the negative 5th. So that is 4.30. All right. So now we want to find pH, and that's going to be equal to 14 minus our pOH. So that's 14 minus 4.30. So you will get 9.70 for your pH. Okay. There is a pH and pOH worksheet for you to try some of these problems on. And some of the later problems are a bit more complicated, so I will have a video posted as well going through the solutions of those for you.